Here we're going to look at question 9 from section 2 of the ENGAA 2018 paper. In this question we're given the following circuit, which has a power source of 12 volts and then 6 resistors with a voltmeter connected between them as shown here. The question then simply asks us, what does the voltmeter read? Now if you'd like to have a go at this question yourself, please pause the video now, otherwise let's have a go at it. So to go about answering this question myself, when I first looked at it, I thought the easiest thing to do is probably to redraw it, because generally with circuit questions it is. But actually, after looking at it for a few seconds, I couldn't really see an easy way to do this. So I decided we could go another route instead, which was to really analyse the circuit and think about what a voltmeter actually does. So first of all, what is it that a voltmeter actually does? Well, what it does is it tells a potential difference between two different points in a circuit. So normally what we'd do is attach a voltmeter in parallel around about one element, and it would tell you the difference in potential from one side of the element to the next. So what our voltmeter is doing in this configuration is it's telling the difference in potential between this part of the circuit and this part of the circuit over here. So it would be really handy, and basically what we're trying to do for this question is if we could find out the potential at each of these points. So bearing that in mind, let's try and really analyse our circuit. So what do I mean by analyse our circuit? Well, first of all, let's notice that it is a parallel circuit. We've got a row of resistors here in parallel with this row of resistors here. So we can ignore our voltmeter for a moment, because voltmeters generally have an extremely high resistance, so there's basically no current going through this wire, and we can really just ignore that element. In terms of how the current actually, the circuit actually behaves. So in essence, we have two parallel lines of resistors with our battery. So what do we know about parallel circuits? Well, we know that the two parallel elements are going to have the same voltage, and in this case, we know that there's going to be 12 volts across each of our parallel component, which we know because we've got 12 volts across the battery. So Kirchhoff's voltage law tells us that this is going to have 12 volts across this part and 12 volts across here. But what does it actually mean to have 12 volts across a part of a circuit? Well, what it means is we have a current flowing this way through the circuit, and then just before the components begin, we have a potential of 12 volts. And then afterwards, we're going to have a potential of 0 volts. Right, so you can see here that we have 12 volts here, 0 volts here, so the potential being transferred to this part of the circuit is 12 volts. And then this, of course, makes sense with the other parallel component, and this is totally fine. We've just got 0 volts to 0 volts. There shouldn't be any potential difference across this wire. In the same way, there shouldn't be any potential difference across this wire, because no wires in our circuit have resistance. Which would make sense as well, because then we can go back up and we have 0 volts at this side of the battery. So 0 volts up to 12 volts, 0 volts up to 12 volts, and 0 volts up to 12 volts. So this is what's really happening in our circuit. Now we want to try and find the potential at these 2 points at either end of the voltmeter. So one really easy way of doing this, is to find the voltage which is used up, or dissipated if you like, in this resistor. So how are we going to find this? Well, since we've just got 3 resistors in series, then this is just a potential divider. So to find the voltage used up across our 1 ohm resistor, we just go ahead and multiply our 12 volts by our 1 ohm resistor divided by the total resistance of our series circuit. So the fraction of voltage being used up is just a fraction of the resistances, or the resistance of our element over the total resistance. Then, of course, going ahead with this, we find this is just a sixth of our 12 volts, so we have 2 volts being used up across our 1 ohm resistor. So, therefore, if 2 volts are used up here, and we start with 12 volts, then at this point here, we're going to have 10 volts. Which is really helpful, because now we know the voltage at one side of our potential our voltmeter. So now all we have to do is to find the potential at the other end of the voltage meter, which actually we can find really easily, because this part is identical to the first part, other than that it's reversed. But if we were to do the maths and find the voltage across our 1 ohm resistor, we see that actually it's identical to the maths we did here. So we know there's going to be 2 volts across our 1 ohm resistor as well. And if we start with some number of volts, use up 2 volts, and then goes to 0 volts, we know that before our 1 ohm resistor, we're going to have a voltage of 2 volts. So And we know at one end of our voltmeter we have 10 volts, and at the other end we have 2 volts. Therefore, if we want to find the potential difference between these 2 points, the reading on our voltmeter, then all we have to do is take away these 2 potentials from one another. So our 10 volts take away our 2 volts, just gives a reading on our voltmeter of 8 volts. So this is the final answer, and it's going to correspond with answer E given in our question.